All right, let's continue. Just as an introduction, in the last video, we understood that it has 4 octets. The IPv4 has 4 octets. Each octet can range from 0 to 255, resulting in how much? I don't know. What do you mean I don't know? I mean that, or I meant that actually, if you said that one single octet, let's say octet, had a value of 8 bits, and that resulted in 2 to the power of 8, which equals 256, meaning that there are 256 possibilities in an octet. So how many possibilities are there in the IPv4 in total? Same. If this was the number, or let's say the volume of an octet, take the volume of the IPv4 itself, the volume of the IPv4. Okay, so the total is actually 32 bits, and that will take us to 2 to the power of 32, which is a huge number that equals almost 4.2 billion addresses. In the end, they are under the general term, let's say, or the general rule that they are of 4 octets, each octet with values ranging from 0 to 255. One of the most famous IPv4 addresses known and used in the world is, you might have seen it before so many times, or you might have been got bored with it because it has been repeated for 1,000 times for you. Regardless, it's the 192, 168, and let's say it's actually 0.1. 0.1. This is one of the most famous IPv4 addresses in the world. And if you want to re-summarize again what we have seen, 4 octets, correct. 1, 2, 3, 4. Affirmative. Number 2, each octet is of the decimal language. Decimal language, yes, it is the decimal language, because I can see that the number 192 can be built, or let's say derived from the digits of 0 to 9. Correct. Can be summed from the digits of 0 to 9. That is correct. No problem with that. And also number 3, every single octet has a value that ranges between 0 to 255. So we have seen the 0, we have seen 1, we have seen 168, we have seen 192, not a problem at all. And maybe we can see one day 240, 250, 255, but never, you said it right, 256. Never 256. Be certain of that. All right. So this is a number 2 screenshot that I would like to take. That's for you. Take this again. All right. And if we took that, let me just save it for you, and I will proceed. That will be screenshot number 2. Done. So if I went back, what do I have so far? What did I cover from the slides? From what you should care about. What you should care about from these slides so far is that it's a layer 3 technology that is correct. Meaning that IPv4s are transmitted or encapsulated or are part of what? What is the transportation unit? What is the PDU type? Let's say the protocol data unit that traverses or resides or operates at layer 3. Operates is the best one. What is the PDU, the type of data unit that operates at layer 3? You have probably said it right. A packet. That is so good. So far, so good. A packet. Inside a packet, and only inside a packet, you will find and see an IPv4. So what's inside a packet, to be honest? Now, for this one, I will not really, let's say, draw it all again, because there are so many sketches on the internet that are better. Let's say packet, IPv4 packet structure. If I just typed it in that way, consulted Google, went back, or let's say went to the images, so many images of them, some from Wikipedia, others. Is there anything from an official vendor like Cisco.com? There is a Huawei. Fine. Other than Huawei, what do we have? Packet pushers. I have heard about that before. Such vendor or production or manufacturer. Network Academy. Tech Targets. I am looking for something official on Cisco. Nothing from actually here. So it seems that I will loop myself and go back to Wikipedia. Not an issue with that. Open the image in new tab. And let me see. This is of good quality. Actually, it was zoomed in. Okay. So this is a packet structure. What do we have in the packet? We have the header. We have the header. How did you just know that this is the share of the header? What is the header, by the way? A packet has a header, not a label, but like a label, because I can't say a label. There are books in the network. One of my favorite books is the MPLS and the SDN era, talking about the label for 900 pages. So there are books talking about labels, and I should not call this header as a label, but just between you and me, like a label. This is just like whenever you buy something, there is a label on the forehead. There is a tag showing you brief information about the product. Brief information about the product, not the actual info. The actual info are the data. These are called the payload. This share here is the payload. Whatever inside the packet, the true reason for sending the packet is the payload. But the brief info about the packet is the first 20 bytes. So I asked you, which should be the opposite, you asking me 2 minutes ago, how did you just know that the share of the packet header starts from this point and ends up here from the 20 bytes? Because it's fixed with the IPv4 packets. The first 20 bytes are taken, fixed, reserved, deducted for the header itself. So look for the very first 20 bytes. This is the IPv4 header. There are so many fields to be filled in here. Of course, I'm filling nothing but by myself. The computer world is doing that between the components, a router and a multi-layer switch, a firewall and a router, a server and a switch, a computer, whatever device, in the end, the same. So one of the fields is the version. We are talking about IPv4. Another version, let's say, or another field is the type of service. When you study quality of service, you need to know that. The total length of the packet. Okay, we might see that someday. A fragmentation offset, if you ever study that in the future. The time to live for the packet depends on the type and the vendor operating this. The protocol carried at layer 3 and layer 3 only. It's not our lesson today, but just briefly. The numbers that your eyes might see in here ranges around between 0 to 255. Is that related to the IPv4? No. This is just another coincidence, another 8-bit value, a possibility of 8-bit value, meaning that there are so many protocols in the world, like EIGRP, if you ever heard about that, or you will hear OSPF, GRE, ESP, ICMP, so many others, a lot, tens, all right, but they range or they are around 250 protocols only. Where is the catch? Protocol number 6 refers to TCP, which will open a door to the layer 4 of the OSI model, and you will have thousands of possibilities there. Protocol number 6. Protocol number 17, not 7, 17 refers to UDP, which will open another door for IPv4 with thousands of possibilities of supported protocols that were architected or built over the technology of UDP. So again, this field that you should study later, and you should carefully study it later, can have around 250 possibility, around 250 possibility. Some of them are for protocols that just operate there at layer 3. Protocol 47, GRE tunnel, it operates at layer 3. It does not need any further, let's say, layers or an escalation or a further decapsulation, let's say, over layer 7, 4, 5, 7, 6, 7, no need. It operates at layer 3. IP protocol 47. If you ever saw 50, it's the ESP, encapsulation security payload, to encapsulate and encrypt your payload. If you ever saw 88, EIGRP, a routing protocol that operates at layer 3. If you ever saw 89, OSPF at layer 3. If you ever saw 6, means TCP, but in layer 4 you will find the number 178, meaning it's a BGP. So there are so many possibilities. The idea is that you either see a number of protocol that operates at layer 3, or you might see 6 which is a door to TCP with its thousands of possibilities. 17, a door to UDP with its thousands of possibilities as well. Now let's leave it to here. That should be enough. What I wanted to show you is that from these 20 bytes, we have here and here 4 bytes for the source IPv4 address, 4 bytes for the destination IPv4 address. How did you just set 4 bytes? Well, because a single IPv4 take 32 bit, and converting from a bit to byte should be by, let's say, dividing on 8 by 8. So every single byte is 8 bits. 4 bytes are 32 bits. And since things here are volume based, then we are definitely talking in bytes, not in bits. That's why it's referred to, even bits are the same, but it has its own uses. That's why if we talked about a source IPv4 address, it is either 32 bits or 4 bytes. When we talk about the destination IPv4 address, same, 32 bits or 4 bytes. So I needed you to understand this. I needed you, and I wanted you to see that. I wanted you to know that there is an IPv4 packet. It has to be a packet based on the IPv4 technology inside the Ethernet frame, the technology of the Ethernet. And this is layer 2 speaking. Going down to layer 1, you will need an Ethernet cable to carry your Ethernet frame. An Ethernet cable, nowadays, we are in 2023. We are starting the third decade, or at the first third of the third decade of the 21st century. We have the copper cables, also known as twisted pair cables, and the fiber optics. These two are the type of cables that are supporting physically as wired in the wired network, supporting the Ethernet frame. The Ethernet frame can carry the packets designed, or let's say the IPv4 packets. Also, the wireless is included as well in the Wi-Fi technology and some other microwave, etc. So this is talking about the packet, and we have already talked about many, let's say, nodes so far until today. Decimal language, logical address, 32 bits, 4 octets, later. We need to understand the conversion later. This will have to do it again. And we have known that the total amount of IPv4 available in this world so far are almost 4.2, or let's say almost 4.3 billion IPv4 addresses. That will be more than enough for you. Just refresh your idea, understand the basics of the very first basics before we start a little bit more heavy work in the upcoming lesson. Because the upcoming lesson, when I'm talking about subnetting, I will directly start some technique called the VLSM, the variable and subnet mask. And this will be a door that you will wish to end so very soon, but you will enjoy it, I promise you.